My name is Karl Ochsner. I am since 40 years in the heat pump business when I created my company. In the main company, we produce some 10,000 units per year, small capacities and large capacities up to 1 megawatt and to temperatures up to 130 degrees. With our sister company, Ochsner Process Energy Systems, called OPES, we also were part of this project ReUseHeat, recovery heat from metro systems. And I am glad to present you some slides on the work we did. At first, I would like to say that there is a lot of potential in the metro systems because we have in Europe some 37 cities where metro systems are. And of course, there is a lot of ambient air in the tunnels. Where does the air come from? The warm air come from? Yeah, from the drive of the trains and from the brakes of the trains. Once you accelerate, you have to brake down. All this needs energy, produces waste energy, and of course, the heat the passengers emit. All this heat is now wasted today, is dumped through the ventilation systems. And if we use this heat, we can transfer it for heating grids or special buildings, depending on where we are located, where we are situated. When we feed the energy, the heat into buildings, we roughly need it for heating in the heating season. That means some 2,000 operating hours per year. But when we have the chance to feed into a heating grid, then we have the chance to operate the heat pump some 8,000 hours per year and deliver much more heat. When we look at the temperatures with the heat pumps today, we can achieve almost any temperature level, low temperature levels like 60 degrees, 70 degrees, or medium temperature levels like 70, 80 degrees, 90 degrees, or even if required over 100 degrees. Of course, the amount of CO2 emissions reduction depends on what temperature we need, because the higher temperature we need, the lower is the COP, the coefficient of performance of the heat pump, and the more power the heat pump need to be driven. That means when we supply to a high temperature net, we save a little less CO2 emissions compared to feeding into a low temperature grid or low temperature heating system in the building, then we can save more CO2. This is just an introduction, but now I will go through the slides.
Madrid Subterra is an association that promotes the use of energy created in urban underground infrastructures as a result of their operation. In particular, we promote the recovery of metro waste heat. In the case of Madrid, our metro network is about 249 kilometers long and has 302 stations. Annually, it consumes around 546 gigawatt hours of electricity, and from this, there is a production of about 400 gigawatt hour of heat per year, which is more than 1 gigawatt hour per day. The advantages of using this heat are very interesting. First of all, we are using an energy which is normally disregarded, so we're talking about energy efficiency. Second, this is a local and distributed energy. It helps in reducing the energy dependency in cities. We are talking about a clean energy as well. Using it avoids CO2 emissions, contributing to decarbonization. And finally, we use a heat which is thrown into the atmosphere, so we avoid thermal stress and heat island effect. Based on these aspects, we believe metro heat recovery can be a very useful energy vector for the future. Thank you.
I will share the experiences we had I will tell you about the challenges and the lessons learned. I think this is one of the most important things here, the lessons learned. It was not easy. Yeah, by the end of 2018, Vattenfall proposed that OPES will take the role of Bucharest metro system, because Bucharest metro system did quit our project, and we were supposed to find a place where in the metro system of Berlin we can install a heat pump. We have been in many locations, in many stations, and seen many tunnels to look for a suitable location for the heat source, and of course, for a nearby heat user. We found then the first most suitable location at Ernst-Reuter-Platz. You see it here marked in yellow on the map of Berlin. At the left-hand side, you see the entrance, the main entrance at Ernst-Reuter-Platz. At the right-hand side, you see the university, the technical university, where we would have been able to supply the energy to. We have also visited some other locations, Frankfurter Allee, left below, or Osloer Straße. But at these locations, it has been more difficult to find heat users. So we decided, yes, we go to Ernst-Reuter-Platz and we make the design of the system there. Here at the top right, you see in blue the station system at Ernst-Reuter-Platz, and in gray, you see the technical university buildings, the campus. It is close by and therefore not a long distance to supply the heat. We, of course, had to choose the right place where to locate the heat pump. At the left-hand side, you see the lower level of the building, where one possible spot of positioning the heat pump was investigated and considered. And on the below, you see the station area. And besides the station area, we have found a room with direct access and next to the tunnel. Here you see the system of Ernst-Reuter-Platz. Gray is the station area where passengers board the trains. And at the right-hand side, you see a side room with a blue cross. There we found the most suitable positioning for the heat pump. And this room was directly, directly neighboring the rails. And so we would have no distance between the heat absorbing unit of the heat pump and the heat pump itself. That's why we could use a direct expansion system. Here again, the rooms. At left, you see the room where we inspected. You see also the openings to the tunnel itself. And there we would have had to install a ventilation, a fan, so that we have a good air exchange between the side room and the tunnel itself. At the right-hand side, you see the heat distribution system of the university, where we would have fed in our heat from the heat pump. At the bottom left, you see part of the university where the Mensa is, and the Mensa would have needed heat all the year round. That means 8,000 operating hours. Excellent, excellent results. But then the distance has been too long for this room, so it was considered to heat the cafeteria at the bottom right, which was under construction, but there we would only have been able to supply heat for 2,000 hours a year. Here you see the sketch of the heat pump system planned and designed. At left-hand side, the evaporator, the fan coil, where the heat is absorbed. Then in blue, the refrigerant line between the fan coil and the heat pump itself. At the right-hand side, you see the hot side of the heat pump with the buffer tank, a storage tank, from which the heating system or the heating grid would have been fed. Here, a top view of the room. At the very top, you see with the gray areas, the rails, and then with the blue arrows, the openings where a fan would have been installed to secure a good air exchange between the tunnel and the operating room. You see here also that the evaporator with the two fans is very close to the heat pump, avoiding any heat losses of heat transfer. And then you see also the buffer tank, and the red lines is the heating line to the building. This is how this heat pump GMLV 35 or Air 85 would have looked. At the left-hand side, the heat pump with the compressor, and at the right-hand side, the evaporator, the fan coil as heat source. Yeah, after we have designed everything and contract ready with the installer, the prices, the details of the designs, and so on, were assumed. And just before we could place the order, we got the message from the BVG, from the runner of the metro system, that we cannot proceed because the staircase, a new staircase was built, and they need this room. Here you see their new planning in yellow at the top. The upper picture, you see the yellow room. That's where the heat pump should have been installed, and a new staircase, Neubauausgang Gleis 1, a new staircase. So they needed this room here, and we had to look for a new, different location. We looked at, for instance, Friedrichstraße. Friedrichstraße is where the border was between East and West Germany at ancient times. Here we could have installed the heat pump easily. You see at the right-hand side, in between the rails, a lot of space, but there was the problem where to supply the heat to. And that's why we went to Frankfurter Allee, and we found, okay, the Frankfurter Allee, the second best option. And because there we had someone who wanted to use the heat, the BVG itself, the Berliner Verkehrsbetriebe themselves, because they heated their building, the rectifier building, up till now, just with electricity, with direct electric heaters. Here you see an air view in the red circle, the rectifier building, and the 100-meter distance to the rails just located below the road. The right-hand side, also the entrance of the rectifier building. And here, again, two more views of the rectifier building itself. At left-hand side, you see the lower level, where the connection tunnel between the rails, the rail track itself, and the building was conducted. A tunnel 100 meters, more than 100 meters long. You see here, it is a very small tunnel with the cables supplying the direct electricity to the trains, the rails. Here you see the location between the rails where the fan coil was to be installed to collect the ambient heat, the heat from the tunnel. And at the right-hand side, you see again the tunnel and all these fire protection walls and doors in the tunnels. So the planning was really not easy, and many, let us say, challenges had to be met and solved. At the left-hand side, you see the problem that there is always train traffic, of course, and to the spot where the fan coil would have been installed, there was access only permitted between 1 and 2 a.m. during the night, with 3 different supervising persons from 3 different security departments of the metro operator. So I need not to tell you how difficult it is to install a system when you go directly to the rails, where the rails are. This is again a view of where the tunnel is entering the buildings with the cables, and at the right-hand side you see the ground floor of the building where the heat pump would have been installed. A lot of space, no problem. Yeah, at the bottom you see where the electric supply cabinet is placed. Yeah, you see on the top view that there is a lot of transformers positioned here in this room. Of course, a lot of weight, these transformers. And the heat pump would have had, where the 2 persons you see, much less weight. But in spite of the fact that heat pump would have less weight, they forced us, they obligated us to ask a consultant to make that complete static calculation if it is possible, feasible to install the heat pump there. That means more and more regulations came, so this delayed, of course, the planning work. And we did not get all these, let us say, restrictions at the beginning of the planning, but only step by step. This was not easy. This is the ground floor, which would have been heated from the rectifier building. And this is the upper floor, which would have been heated with the rectifier building, with a new system of hydraulic heating with radiators. Here you see also at the left top this upper room. And here you see the electric heaters. There were several electric heaters with a capacity of 20 kilowatt. Of course, a little bit of waste of energy when you use direct electric heat instead of grading it up with a heat pump. This is a design where you can better see the situation. At the left-hand side, the tunnel with the trains, and in between the 2 rails, the fan coil to be installed. In blue, you see the hydraulic line, the tubes, which transfer the heat from the fan coil to the heat pump itself. The right-hand side to a low temperature buffer, and then besides at the right-hand side of the heat pump, the high temperature buffer. From this high temperature buffer, the heat supply system, the heat transfer system in the building would have been supplied with the heating energy. At first, Vattenfall said, yeah, we make a contract with the neighboring building too, and we need more heat than just for the rectifier building. That's why we planned a Aqua 97 machine with some 89 kilowatt heating capacity. After a couple of months, we were informed, no, we will not supply the heat to the neighboring building, but only to the rectifier building of the metro operator. Then we replant a new system with the Aqua 54, only 84 kilowatt to heat the building itself. The lessons learned, we had the problem that the responsible personnel within the metro operator and also the heat supplier, the contractor, in this case Vattenfall, changed during the planning period several times. So it was difficult to communicate, and this delayed, of course, the process. The more, let us say, the more surprising and the more difficult to overcome was the regulations and restrictions. We got step by step this restriction, this regulation from the metro operator, and we had all this to incorporate in the planning. And of course, this did increase costs, and delay in the planning, and also installation costs after all. Then the problem is that the energy contractor could not agree with the customer for a heat supply contract. And therefore, we could not proceed, and this was killing the project. The problem is, and you see at the bottom, the dependency on external parties, which do not from the beginning say, yes, we will need the system, we will need the heat, and so to be sure that the system will be installed. In this case here, we can at least make some simulation because we have installed some monitors. Opus has installed some monitors in between the rail track so that we can at least have the results of the temperatures and also the humidity. The humidity is also important. More humidity means more heat source. And then we can some sort of monitor the heat which we could have gotten out of the tunnel. We cannot prove it because the heat pump will not be installed, but we can simulate it. The lessons learned is that with the two different cases, one at the Ernst-Reuter-Platz and one at Frankfurter Allee, these are two different systems. One is direct expansion and one is a water-to-water heat pump with an external fan coil as heat source. And we showed that because we did plan to the end, yes, we have several possibilities and technical systems to use the heat of the metro trains in the tunnels. And of course, we can upgrade the system. The capacities we have planned are comparatively low. Why comparatively low? Because we had not much space to install larger systems, and we had no customers for more heat. Yeah, another key factor, of course, is the temperature level in the subway. For instance, in the London tube, we have much higher temperatures because the tunnels are much deeper in the ground, and the rock cannot absorb anymore the heat from the trains and from the passengers. And therefore, a lot of energy is needed and a lot of air exchange is needed to cool more or less the stations. Here, it would be very important and also very efficient to use this high tunnel temperature for a heat pump.
Hello, I'm Rodrigo Matabuena. I'm the Energy Capital Projects Manager of Islington, and I've been involved over the last 4 years in the Bond Hill 2 project, which is the extension of the existing Bond Hill network in Islington. This extension is now taking heat from the London Underground, from a disused station of the London Underground. And this project has been really, really successful in many, many ways, and we're very, very pleased of having this this project. Two of the key elements of success of this project has been one, the institutional and political backup. Without this political backup, it would have been impossible. This project will take a long time to be, well, it has taken us a long time to deliver, from conception till operation. It's almost a decade. So without this political and institutional backup, it's pretty much impossible to drive this project forward. The other element that I will mention is having a very well-defined governance structure within the organization and the project management team delivering the project. It's very likely people will change throughout the life of the construction of a project like this. So that is really important. And yes, we're rolling out this project. We're thinking about delivering the next stages, not only around Bunhill, but also new heat networks that are also taking heat from waste sources, not only the tube, but also data centers, for example. So yes, we're really happy, and yeah, we're definitely looking forward to see these projects around London, the UK, and Europe in general.
This is the temperature, the ambient temperature in Berlin, which also has, of course, an influence on the temperature in the tunnel and in the stations, because the metro system is not very deep in the ground. And the temperatures from monitoring we will get in the next weeks only from the metro operator, and then we will also publish it. Thank you for your attention.